Okay, so I'm back. Let's continue with our little homework here. Servos of this size, I want to be able to place them anywhere at any rotation, and I also want to be able to draw the links. Now, let's have a look and see how we can do that in Matplotlib. Now you may have noticed that when I drew the arrow, that's fairly straightforward. You just use the plot function, but the problem is plot draws a line only, not a filled shape. So we need to figure out how to draw filled shapes in Matplotlib. That's sort of the exercise here. And let's see, I'll just go ahead. If you filtered out, if you figured out how to do it, then good. Otherwise, you will have to look at my code and then see how I do it. So let's draw our servo. And the width and the height I said was 13 millimeters and 29 millimeters. So now I'm gonna keep everything in meters, just like I keep all my angle in radians. So 13 millimeters would be 0.13, and the length would be equal to 29 at 0.029. I have a transformation matrix, and by default and we draw it in 2D. So the translation and the rotation and things like that I want to represent as a 3x3 transformation matrix. Of course, homogeneous coordinates, by the way, are also used extensively in computer graphics or 3D CAD programs, where often you can specify the exact transformation matrix. If it's a 2D drawing program, then often you can represent the 3x3 matrix, or if it's a 3D drawing program like Blender, if you're familiar with Blender, the very good open source 3D drawing program, that also allows you to specify the transformation matrix as a 4x4 matrix. Similarly, for 3D game engines, they all have 4x4 transformation matrices. 3JS, for example, a JavaScript library to do 3D drawing, also allows you to specify the transformation matrix 4x4. Now here, this one you may wonder why I don't just set this to NPI, which is the identity matrix for 3, which is 100010001, that matrix. The reason for that is that the arguments to a Python function for complex data are passed by reference, which means you can actually override it. So I'm not sure about NumPy, but if I make a mistake in my program and I change NPI to something else, instead of 100010001, then I may actually end up overriding that identity matrix for the entire part of my program, which is not desired. Or similarly, if you want to read in arguments from the command line, so it's better to just say that if it's not specified, it's none, and if it's not none, then we generate a copy by using the mp.i function here. I'm not 100% sure if this is strictly necessary here in Python. It may not be, but it's not a bad policy to make sure that your default arguments cannot be overwritten. The 0.013 here, that one is passed by value, so I could change that if I wanted to without changing the underlying value, the underlying width. So A is equal to none. Now I have an identity matrix Now let's draw the body of the servo motor. Now here I include the patches library. Now the body of the robot, which point should we use as the origin of the servo motor and the orientation of it? So I would say that it makes the most sense to have the center of the servo horn, the disc that rotates, as the origin of the servo, and then have the servo motor in the home position. It's usually centered, and then it can rotate 90 degrees to the right, 90 degrees to the left. So if I want to represent that for a degree of 90 degrees, then the x-axis has to go down here and the y-axis has to go to the right. So that we rotate from x to y along z. Then if I rotate to 90 degrees, then that's the position that I'll end up with, where x-axis is exactly in this direction. So let's see what we can do. The coordinates for the body then are given as a n by 2, so a row vector. So now if I want to draw the shape, then it would be centered and offset. So the width is 0.013, so the first y coordinate would be minus width divided by 2. In order to draw the polygon for the rectangle, I need 5 points. So we have y coordinates negative width over 2, and then we start. Now the x coordinate, that depends on how far the servo horn is inside. Let me just check for the servos that we use. And that would be 5 point 5.5 millimeters. Whole thing is 33.29. So that's 4, so that's 2, so that's 1 millimeter. So 2 minutes, 7.5, 6.5 millimeters. Six five. 0.065. Okay. So then that would be length minus length minus horn x offset negative width over 2. That's my first point. And that goes to horn x offset negative width over 2. Then horn x offset width over 2. Then horn minus length plus horn x offset width over 2, and then back to the start point, negative length. Actually, I think it has a closed function, so that means has a closed parameter. Then it will automatically close it. So we just set close to true. I don't need to pass in the last point here anymore. 4 points are sufficient. So then I want to draw it, so I want to also pass in the axis that I want to plot. Actually, I don't need to pass in the axis because P is equal to M patches dot polygon with the coordinates m by 2 array, closed is true, and then various filters. So let's say edge color is black, face color is equal to, I think we can pass it like that, so dark 50 50 50, and we can also pass in the alpha channel, but we will do that later. Fill is equal to true. So then here we could specify some default parameter. Right now I just set it to the empty dictionary. And this is how we can pass them on to matplotlib, and then we return p. Okay, so let's test it out. And I haven't done anything yet with the transformation matrix, you may have noticed. And then let's just call it I think it's add patch. P. And I think the problem with patches is it doesn't set the width of the axis. So we need to set that manually. So let's go from -1, 0.5 to 0.5, so 50 centimeters and also 50 centimeters in the y direction. That of course has to be a 2D array. Okay, so here we have our patch. Now we have a little servo motor there. I'll make it a little bit smaller. Here we have 0, 0. 0 would be here. So that's the first part of the servo. Now I want to draw the circle. For the servo horn, if you've never seen a RC servo or any other kind of servo, this is what they look like. Like here. This servo actually has a cross as the horn, but we also have the discs. If you want to, you can also add a cross to your visualization. So you have different horns you can attach here. Here's the standard round circle horn. And yeah, they're quite cheap if you buy them from Amazon. $1 or $2 each. The problem is if you buy them, then they come from a cheap company in China that makes them, and lots of people bought 10 and then 3 were already dead by the time they arrived, so it's a little bit hit or miss. And here you can rotate them. So this is what they look like. Now where's my... Okay. So there's another another patch for the circle. So we can draw the circle. So that has the center. So the center should be 0, 0. And the radius, which is equal to 0.00, what did I say? 20 millimeters. So 2 centimeters, 0.02. And that was the diameter, so the radius would be 0.01, 1 centimeter. Fill equals true. You have fill, edge color, and face color. So edge color is black, face color is white, pretty white, so F0, 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 and filled. And then we return the P and the C. Let's see. So here we have a servo motor now with our horn, our body, and it looks reasonably good. So now I want to be able to place that anywhere on the playing field, and I want to be able to rotate it. Not anywhere on the playing field, anywhere on the canvas. So okay, that means here we need to change Now, given the discussion before, you should have figured out that what we want to do is apply our transformation matrix A to these points here. A is a 3 by 3 transformation matrix. So A, we need to have these points in homogeneous coordinates, so I need to extend it with a 1. And I also need to multiply them. Now they will be in row coordinates. So let's see if that works. So here I want to append the coordinates and length of the coordinates here. And now I better print it out because those H stacks and V stacks are sometimes a little bit tricky with NumPy. Pen dispatcher. Not NumPy append, I think. Not a tuple. Expected to. Oh no. Yeah. Then H stack. Now with VStack that works. That's what I usually do. So I transpose them and then add the ones to it. I'm never sure why HStack doesn't work. So now these are the column vectors. And that's okay now. Now I want to now when I draw them here, I need to take the coordinates in the transpose to convert them back into row coordinates, which is what Polygon wants. And then I want any row and columns 0 to 2, 0, 1, but not 2. now we're back to where we were before, and we're drawing. Now I want to apply our A matrix. So this means I need to apply that and apply A dot. Oh wait, I do it in a separate line so it's clearer. Okay, and now so now we want to have some functions to, well, we just want to use the functions that I wrote before for the homogeneous coordinates. So here we take those two, translate and rotate. So servo 2 is a servo that I want to draw at position 5 centimeters to the right and or 15 centimeters to the right, 15 centimeters up, and 2 centimeters, 3 centimeters to the right. Now we should get 2 servos, one here and one there. But I made a mistake. I didn't add the circle here yet. So the circle position and the radius must also be added. So the center of our circle is at A dot And then that's the origin. I wanted to draw it originally at the origin, so so I need a column vector here for 0, 0, 1. So I want to draw that at the center. Now we have two servos, one at 15 centimeters up, 2 centimeters to the right. And now I want this to be the shoulder sensor in this frontal plane. Let's say I want it to move like that. Then, okay, I want to the arms. Yep. So where are we here? Center, yeah. I wanted to rotate it by 90 degrees, yes. So now that means this shape here, I need to rotate counterclockwise. So first what I want to do first is rotate it and then translate it, which means that the rotation has to occur here, and I want to rotate it by 90 degrees. Rotate is not defined. Rotate Z. And now the servo is at the right position and it's also rotated correctly. I can also rotate them now by arbitrary degrees around a point. So let's move this servo to minus 0.03, and that's the point that I want to rotate it around. So I translate 0.3 negative 0.15 for the points, then I rotate it by 90 degrees and then I translate it back. So now that will be, it rotated by 40 degrees just to show that also will end up the same. No, rotated out of view then, I think, 30 degrees. And servo sit 3 here. So now we can have a servo there. So that's pretty neat. Now I only want to be able to draw links. Now drawing links is very similar to drawing the servo body, of course. So I could just use that function and generate classes for servos and links. And we may do that in the future, but at the moment, for today, we'll just leave it at that. So I want to draw a link, the width and the length of the link. There's no offset for the horn or no radius, and some additional parameters. And for the link, the question is, where do we put the origin? And I think what I would like to do is, eventually in the future, I want to have the links being rounded. So I need to have the caps size there. Then the left part is the start of the link and the angle, and that will be the head of the link, and then the tail of the link is somewhere here, somewhere out there. So I leave the radius here, but this is the radius of the half circle around the link. And what did I set for default there? 0.0065. So make that one smaller, 0.003. And I'll add that later on. So what I want to draw is the link starts at x location 0. Negative width over 2 goes to length. Goes to length. And then goes to 0. Now the colors, let's make it, in the figure that I had it was a little bit yellow, so let's make it yellow. Let's try F and F. I'm not sure if this is RGB or BGR. So that's okay. We'll just experiment with it quickly, and I don't need to draw the horn. And I'm still going to return it as a list so that I can extend it independently of what it is. Okay, that looks good. So let's make the width of the link 3 centimeters and the length 6 centimeters. Okay, the brackets, I think I have to turn it like a list then. Okay, oh, much too short. Oh, 0.15. Oh, that's a position. Oh, that's okay. And oh, I didn't pass in though. No, I passed in. Oh. Yeah. 3 centimeters and 6 centimeters, not 3 millimeters and 6 millimeters. So here's our link then. And now I can also rotate that. Use the same rotation matrix. And the link maybe a little bit smaller, 2 centimeters and one 10 centimeters long. Now we have this here. Maybe I make the link smaller. Oh. Here's radius. What is this? Keep going. Ah, I changed the wrong numbers here. Yes. That should be 0.3, 0.15. This is 1 centimeter and 10 centimeters. And link 1 is also 1 centimeter and 5 centimeters long. And there we have those. And let me just, for the future, make sure that we set the aspect ratio to be equal, so that the circles look like circles. Right? Okay, so that's it for today. Can draw. You can now think about how to do this in 3D, for example, but we're going to do some more visualizations in 2D, and next class, Monday, we will be starting to work on forward kinematics, which means if I have a humanoid robot that I built, then how can I actually come up with motions that my robot can follow. Okay, so bye bye.